Welcome back to Cath Lab Outreach. My name's Scott. Today we're going to talk about right heart caths. So right heart caths are a completely venous procedure. We talked about left and right heart caths in a previous video. Today we're going to focus more on the right heart cath aspect. And one of the things that you want to collect in a right heart cath are the pressures inside of the different chambers of the heart. So usually you're collecting pressures and you're collecting oxygen sats. And when you think about the right atrium, as a former firefighter, so when I think of fire pump terms, your right atrium has three intakes. It has from above the heart, the superior vena cava, from below the heart, the inferior vena cava, and it has one more, coronary sinus. And that's where the blood that fed the heart muscle itself comes back to that right atrium. So one of the things you talk about with sats is if we measure sats in the vena cava, and let's say up here and down below, let's just say it's 60, the oxygen saturation is 60. When we get into the right atrium, all of a sudden it's 72. Well, how do we go from deoxygenated blood to partially oxygenated blood before we made it to the lungs? Well, we have some type of mixing going on. So that would be a shunt, and that would be the most likely place for that type of mixing is from the left atrium coming through the septal wall to the right atrium. And PFO, a patent foramen ovale, is a key cause of that. You could have an ASD, an atrial septal defect. And these are holes between the atria. We close these on people in their 60s and 70s. Why are we just finding that out? Well, if there's never a problem, you never go look. But your primary problem that sparks you to go and look for these issues with an echo most of the time is a stroke. So if you have a cryptogenic stroke, now we don't really know where this clot came from. You go start looking for it, and the heart's a big part of that. AFib, causing the clots to form in the left atrial appendage and then going to the brain, or this turbulent flow between the atria. So measuring sats throughout it's called a shunt run, but measuring sats throughout the body in different areas gives you a lot of information. And then kind of committing the pressures to memory, it's a little bit easier with this mnemonic. I found this in some of the study material. It's just too good to pass up. But your right atrium, your left atrium, your right ventricle, and your left ventricle. Remember, you're looking down on the patient's chest, onto their heart like that. So a mean of about 5, 10, 25 should be your systolic pressure, and then your systolic pressure should be over 100 for this. So that was an easy way to remember those things. Nickel, dime, quarter dollar. So this program is RHC Mentis, and this is a program I demoed in one of the other videos talking about heart caths. This is about, I forget actually how much it costs, maybe $25, $30. It's for iPad for sure, maybe used for other things as well. But this is an app that you can buy, and it'll actually let you practice with this, seeing these numbers, seeing these measurements. It also has prefixed scenarios in there to show you what these numbers are going to do with mitral stenosis or other things that you may find, pulmonary hypertension. So here you've got your EKG, and that helps you time out with different parts of the wave. And here is your the demonstration of what is actually going on the inside. And you also have your balloon and your catheter that you can manipulate. So it's a really cool little device. And on this, we see here the sheath, and we got the catheter coming in. Once it's through, we'll inflate the balloon. And it's called flow directed. So this is the flow of blood is supposed to help float this balloon in the direction that you want to go. So here in the right atrium, we'll have a right atrial waveform. We go through the tricuspid valve, and now we see a distinct change of our ventricular waveform. Through the pulmonic into the PA, there's an arterial looking waveform. We'll go out and we'll actually wedge in the pulmonary arteriole, and now it goes back to an atrial waveform. Why another atrial waveform? Because this represents the left atrial. We'll talk about all of these in depth, but any arterial waveform is going to look the same, whether it's PA or if you're in the arterial side and you see the aortic waveform. All of your ventricular waveforms are going to look the same, whether it's your LV, if you were doing a left heart cath and you got into the left ventricle, or your RV in this situation here. The pressures will just be different. And same thing for your atria. Your wedge and your right atrial pressures, those waveforms look very similar because they both represent atria. So let's jump into that part. Here's our right atrial waveform. And when you time out your A wave, that's timed late with the P wave. Remember, your electrical activity is going to happen a few milliseconds ahead of your mechanical response. So late in the P wave, we'll have our A wave talking about the atrial contraction. And that tricuspid valve stays open the entire time. What actually closes that? Well, it's that pressure, that ventricle squeezing. So the whole time it's open, it's just free feeling. And then you'll have your atrial kick, your A wave, which actually, remember we talked about that Frank Starling law where you're stretching that ventricle. And that's why preload is very important. And that's why atrial kick and synchrony with your atria and your ventricles are very important, because it stretches that ventricle and makes it pump that much more effective. You'll have a C wave, which is very hard to see on a lot of these cases, but that's actually the tricuspid valve closing. Think about where this catheter tip is. It's sitting in the right atrium during this waveform. So you think about your ventricular effect. Well, it's not going to look the same as if you're in the ventricle. It should be shielded by the tricuspid valve. So this is what all these cardiac cycles look like from the right atrium. Then you'll have a V wave if you tricuspid regurg, because you're letting blood go backwards from the right ventricle to the right atrium. Other than that, you should just see a little bit of a bump there as remember the right atrium is shielded from the pressure of the right ventricle in a healthy heart, but the blood is still returning to the heart. So as it starts to fill up with that tricuspid valve closed, the pressure is going to start to increase a little bit inside that right atrium. And here's a slow motion example here. You get your, there would be your V wave. Here's your ventricle expanding, so it's filling. And then you have this last little kick here of stretching that muscle, and that's your A wave. And then once that A wave happens, now your ventricle is going to fire, closing all the valves back up, and this will start to fill again. So here's your RV waveform, and your RV waveform looks just like your LV waveform, except your pressures are a lot lower. Remember, your left side of the heart is your high pressure side. The right side is the low pressure side. So important numbers and characteristics of these waveforms that we need to collect here. You may see an A wave. That A wave should be the same as the A wave that is in the right atrium. And so that if that pressure is different, there's something going on with that valve. So your A and V waves help you understand how a valve is functioning. Your EDP is your end diastolic pressure. And this is measured more frequently in your left ventricle, but the right ventricle has one too. And you're talking about, when you talk about diastolic heart failure, you're talking about failure to relax. How does a heart fail to relax? Well, remember, relaxation is an active process. That's why rigor sets in after we die, because we don't have the energy to break those connections until those connections decay over time. So your end diastolic pressure gives you an idea of how much volume we're dealing with, but it also, what can this heart handle? Chances are you could put a liter of fluid in me, IV, and my ventricles are just going to expand. They're just bags, and they'll just expand and take that fluid. But if I have diastolic heart failure, now I don't have bags, I have pots. So when you overfill a pot, now it instead of spilling out on the ground in the ventricles, they're going back up to the previous atria that was feeding those. And that's where our pulmonary edema comes from the left side backing up, or our JVD and pedal edema coming from the right side backing up. So our normal pressures here, we should see a pressure of about systolic pressure of about 25 on this. Here's in this example here, you can see this is elevated pressures. So this is that tall waveform, and this is your isovolumetric waveform because it's changing pressure so quickly, because as it starts to squeeze, it's shut the tricuspid valve, but has not generated enough pressure to open your pulmonic valve. So this vertical part of your waveform is called your isovolumetric waveform or phase, because the volume hasn't changed, but the pressure has very quickly. Your PA waveform looks just like your aortic waveform, except it's a lower pressure. And here the systolic should match your RV systolic, because that's where your systolic pressure is generated from that main chamber. So as that chamber creates that energy, it should all be transmitted through that pulmonic valve. So studying your systolic pressure here gives you an idea of how that valve is actually functioning. And then once that pulmonic valve closes, you have your dicrotic notch. Your aortic waveform has a dicrotic notch as well, except that's from the aortic valve closing. And this one's pretty simple. As we get our pulmonic valve opening from the systole of the RV here, we get that spike, and then as the ventricle starts to expand, blood flows backwards, catches these parachutes of these valves. Remember, these valves are very thin. If you've ever done a pig valve lab, you can actually put your finger behind those valves and see your finger through that valve. They're very, very thin. So as that blood starts to transition backwards, that's what actually catches the valves and slams those shut. And you can actually see that on echo. If you have put color on, you'll see that blood change direction just briefly. As that ventricle starts to expand, it pulls blood backwards just a touch, because it's pulling blood from the atria. It pulls a little bit of blood back from the pulmonary artery, but it catches the valve parachutes, the valve leaflets, and slams those shut. Here, when you marry these waveforms up, your RV and your PA, what you get here is we talked about that isovolumetric portion of a waveform. You have your pulmonic valve opening inside of the waveform for the RV, so that's called an anacrotic notch. You have your systolic pressure, which should all be generated and transmitted into your PA. And then you have your pulmonic valve shutting, giving you your dicrotic notch. And then our wedge waveform, that balloon that's inflated actually seals off in a small arteriole of the PA, and it only lets the tip of that see the pressure that the left atrium is pushing back. There's no catheter to get you into the left atrium. The only way, if you're going to do work in the left atrium, working on the mitral valve through the catheter, or working on pulmonary vein isolation or left flutter, anything you're going to do over there requires a transeptal stick. So instead of doing a transeptal stick just for a right heart cath, the pulmonary capillary wedge pressure, the PA occlusive pressure, those are all different terms you'll see for it. What it does is that balloon isolates the PA's effect, pulmonary artery's effect, and it only sees what that left atrium is actually pushing back through that lung field. In fact, if you draw a sat from your wedge, it should be oxygenated, because if you had a good seal on that wedge, a balloon, the blood you're pulling is from the left atrium coming back through the lungs, and it should be fully saturated. And then you can trust your waveform there. But other than that, it's the same numbers as far as the right atrium, except it's timed just a few 80 to 120 milliseconds later, because it's not seeing the left atrial pressure directly. It has to come back through that capillary field to make it back over there. Once again, a very high V wave would be influenced from the right ventricle. The mitral valve should shield that, but if you see it have a large V wave in there, that's mitral regurg for blood flowing backwards. This was a little harder to see, to time this out, but you have your A wave, and then you'll see a V wave, and you'll know it's a V wave because you'll see your pulmonic valve open here, and a V wave would open that. So there's your V wave coming in. But remember, this is being measured from the atrium, the left atrium specifically, so it doesn't see as large of a V wave. So when we talk about this Swan-Ganz catheter that we're floating through here, This is what the tip looks like. This is where your thermistor, I just call it a thermometer. Well, it's not a thermometer. It's wiring that changes conductivity based on temperature. So here's where your thermistor hooks up for thermal dilution, cardiac output. We'll talk about that. Your PA distal, that's at the very tip of the catheter, and then your proximate injectate. Here at the 30 centimeter mark is where that prox injectate port opens up, and then the distal port is at the very end. The markings on here are very simple. Each tiny mark is 10 centimeters. This is 100 millimeters, so 10 centimeters is each of those marks. Once you hit your fifth one, then you get a bold mark, and that marks 50. So that would be 60, 70, 80, 90, and here's 100. It's got two 50s there. So that would be your 100 centimeter mark. And that's when you secure that for patients that you're leaving it in, that's how you can mark where it actually is. And here's the balloon. It's deflated, but that's where the balloon sits. So some formulas that we can use during right heart caths, between the pressures we get, the sats we get, and the hemoglobin that the patient has from lab draws, we can actually do Fick cardiac output. And what that does is that looks at how much oxygen is being consumed and how much oxygen is still remaining in the blood coming back to the heart. And from that, you can calculate what the cardiac output is. So here, your consumed oxygen, there are some very fancy ways to get that measured directly, but most of the time they'll use just a standard formula, 125 times the person's body surface area. So that will be your oxygen consumed. This 13.4 is a standard. That's how many milliliters of oxygen a deciliter of hemoglobin can hold. How many grams per deciliter of hemoglobin actually is there? What's our sat when it leaves the heart? What's our sat when it comes back? And by doing that calculation there, we can actually come up with our cardiac output. So the things that the computer is going to need, your body surface area. If you're in the cath lab and you're not getting the numbers you need, chances are you forgot to put in your height and weight. That's very common. You'll need the hemoglobin, the AO sat, and the mixed venous sat. Your mixed venous sat is the sat. A lot of places we will use the PA because that's the place right before it mixes. A truer one is mixing, averaging out IVC and SVC mixed from all areas of the heart right before it goes back to the lungs. Another thing we can do is we can compare pulmonary flow and systemic flow. They should be equal. If we have a hole in the septum of the atria or the ventricles, if we have the hole there, we can actually determine that the volume of flow is different. If the blood goes from the left atrium back to the right atrium and goes through the pulmonary circuit again, your pulmonary flow is going to be greater than your systemic flow. So you can use, that's called QPQS. And what you're doing is it's the same formula we use for Fick cardiac output, but you're doing just the PA or just the pulmonary system and then just the systemic system, and you're comparing those. So when you take the same formulas and you mark out what's the same, you're left with your pulmonary vein minus your pulmonary artery sats times QP, AO sat minus your mixed venous sat times this QS. And what you're left with is your QPQS is your AO sat minus your mixed venous divided by your pulmonary vein sat, so with your PA subtracted from that. And that's your QPQS. So you'll need a PA and a pulmonary vein sat, so a wedge sat. You'll need an AO sat and a mixed venous sat. If your QPQS is greater than 1, your shunt is left to right, meaning left atrium to right atrium. If it's 1, there's no shunt. And if it's less than 1, you'll actually have a right to left shunt. And then finally, one of the other things that you'll get from this is your thermal dilution cardiac output. This is done with that proximal injectate port. And what you do is you'll hook up the thermistor cable that hooks to your swan will actually hook up to a thermometer measuring what the temperature of the saline is in the room you're in. And then that'll hook up to your temperature port on your monitor. And when they injectate, you'll see this deviation of temperature, and then you'll see it slowly return. It's actually very complicated, the formula that's behind this. And this is old technology. This was done in the 50s, 60s, 70s. So this stuff has been around for a long time. It's gotten simpler. The technology and the equipment has gotten simpler, but the calculation behind it is still quite impressive. But as that temperature deviates from the body temperature and the body warms it back up, this will actually calculate cardiac output. Then you can compare your thermodilution cardiac output with your Fick cardiac output. All right, that's kind of a basic overview of right heart caths. I hope that was helpful, and we'll see you next time.